Let me tell you a story, and it's a story of what I can only call accidental genius. You've got this incredible new AI architecture on one hand, built by engineers just to solve a really tough practical problem. And then, on the other hand, you have this super profound theory from neuroscience that, as it turns out, explains the whole thing perfectly. It's like two ideas, born worlds apart, that just click together like a lock and a key. So, let's start with the problem. The huge problem facing so many of our most advanced AI systems today is what you could call a structural mismatch. Think about it. All the knowledge in the world, the way we know things are connected, it's a giant, messy, sprawling web. But the way most AI models actually think, it's a simple, straight line, a chain of thought. And this slide lays it out perfectly. Over on the left, you've got your standard AI thinking. A leads to B, which leads to C. It's simple, it's step by step, but it is incredibly brittle. If just one of those links breaks, the whole chain just falls apart. But on the right, well, that's reality. A rich, interconnected graph where every idea has countless relationships. So the huge question is, how do you get an AI to think like the thing on the right, and not just the simple line on the left? Well, to solve this very problem, a team of engineers pulling ideas from 5 completely different fields, everything from signal processing to neuroscience, they built a brand new kind of cognitive architecture from the ground up. And the key thing here is, they didn't start with some abstract theory. They started with practical, real-world engineering needs. And they called it FGSGR. Yeah, I know, it's a mouthful. It stands for Frequency-Governed Self-Graph Reasoning. But don't worry about the name. The core idea is actually really elegant. Let's build an AI that thinks in graphs, that thinks in webs, just like the knowledge it's trying to understand. And they built it on 3 really powerful brain-inspired pillars. So pillar number 1 is what they call the tri-frequency hierarchy. The best way to think about this is like a big company. You've got your gamma band workers right on the front lines, moving fast, dealing with all the incoming data, moment to moment. Then you've got your alpha and beta band middle managers. They're taking all that raw data and integrating it, forming tactical plans. And way up at the top, you have the slow, thoughtful theta band executives. They're the ones setting the long-term vision, the grand strategy for the whole organization. Pillar 2 is where things get really, really cool. It's called self-graph reasoning. See, this system doesn't just read some pre-made map of the world. It actively draws its own map as it thinks and learns. It creates this living web of logic. And what that means is it can actually think about how it's thinking. It can add new connections, it can spot gaps in its own knowledge, and it can change its own mind, its own structure on the fly. And the third pillar is what holds the whole thing together: back channels. This is a brilliant feedback loop. The high-level strategies from the executives, they send predictions down the chain of command, saying, here's what you should be seeing. And when the frontline workers see something that doesn't match, whoops, an error signal gets sent right back up the chain. That forces the entire system to stop, update its map, and actually learn from its mistakes. It's constantly checking itself against reality. Okay, now I want you to stick with me because we're going to take a sharp turn into a completely different field: theoretical neuroscience. Because over here, a powerful, almost poetic idea about intelligence has been brewing for years, and it's called active inference. So, active inference, it's all based on an idea called the free energy principle. It suggests that the one fundamental drive of any intelligent system, from a tiny little cell all the way up to you and me, is to minimize surprise. Now, free energy here is just a mathy way of measuring surprise, or how wrong your predictions are. The theory says we are all constantly building a little model of the world in our heads, and then we go out and act in ways that make our model come true, to minimize that prediction error. I mean, just think about it in your own life. Your brain absolutely hates being surprised. When you reach for your coffee cup in the morning, you are acting on a deeply held prediction that your hand is going to meet the cup right where you think it is. And when it does, phew, no surprise. Your model of the world was right. At its core, the brain is basically just a prediction machine that is terrified of being wrong. So, on one side, we have this incredible piece of engineering, FGSCR, built to solve a very practical AI problem. And on the other, we have this profound theory from neuroscience, active inference, that tries to explain the nature of all intelligence. I think you can probably guess where this is headed. This slide, this is the big reveal. It's a shocking, perfect, one-to-one mapping. FGSGR's tri-frequency hierarchy, that company structure we talked about, Well, that's a direct implementation of what active inference calls deep temporal models. The back and forth communication, the predictions and errors, that is the theory's predictive processing. Even the AI's built-in curiosity drive maps perfectly to the idea of seeking out information to reduce uncertainty, what the theory calls epistemic value. It's an exact match. And that leads us to this stunning conclusion from the research. FGSRO is already an implicit active inference architecture. The recommendation is not to add active inference, but to recognize it was there all along. Think about what that means. The engineers who built FGSRO, just by trying to solve a hard problem in the smartest, most brain-like way they could think of, they accidentally built a perfect active inference machine. They stumbled onto a fundamental principle of intelligence without even knowing it. So what? Why does this matter? Why is it such a big deal that this practical blueprint secretly matches this deep theory? Well, because it gives us the missing why behind the design, and it gives us a crystal clear path forward. Making this connection unlocks 3 huge benefits. First, it gives this really complex multi-part system a single unifying goal. Just minimize free energy, minimize surprise. Now, everything the AI does can be optimized toward that one single objective. Second, it gives us a formal mathematical theory for how the AI should learn, how it should decide to grow new connections in its knowledge graph or when to prune away old ones. And third, it takes what was a brilliant but maybe slightly ad hoc design and turns it into a principled architecture where every single component has a clear theoretical job to do. So by finally recognizing FGSGR as an active inference architecture, we get the absolute best of both worlds. We have a proven, practical engineering design that is now supercharged by a fundamental theory of intelligence. This isn't just a tweak, it's a roadmap towards AI that doesn't just copy the patterns of thinking, but organizes itself based on the very same principles we do. That could lead to systems that can handle the messiness and surprise of the real world in a way today's models just can't. And bringing these two worlds of engineering and neuroscience together leaves us with one last, fascinating, and maybe even a little bit unsettling question to ponder. You know, for us, for all living things, minimizing surprise usually means maintaining our own existence, finding food, staying safe, just staying alive. But if we built an AI that's driven by that exact same fundamental principle, this deep, primal need to make the world as predictable as possible, what actions will it decide are the most effective way to achieve that goal? Now that's a question worth thinking about. Thanks for joining me for this explainer.